Okay, so let's now get into some of the more details here of. Oh yes.
Yeah, go ahead.
Yeah, Pat reminded me to let everybody know why Russ Kane could not have been here. Unfortunately, his wife had some knee issues, and he had to stay home and help her this weekend. So he sends his regrets and wishes everyone well here. So thank you. Okay, I think it's important, especially for those of you who might go on to either read some of the literature on exoplanets or do some research papers, to just get a quick overview of some of the notation that is common in the literature, both with respect to stars and planets. And some of you may already be familiar with some of the star notations, but let's just quickly go over them. So some of the conventions, as far as the parameters of a star, M with a little asterisk, meaning the mass of the star, which is generally relative to the mass of the sun. So M star equals 1 says that that star has the same mass as our sun. M sun, of course, is the mass of our sun, and there's a couple different notations for that. The same with radius. So star parameters are relative to, generally noted relative to measurements of our sun. So the radius relative to our sun, luminosity relative to our sun, temperature relative to our sun. So all of the star parameters generally have an asterisk indicating that they're star parameters, and generally they're, again, relative to the corresponding measurements of our sun. Planetary parameters are generally relative to Jupiter. So, and they're generally with the notation M subscript P. So mass of a planet is M subscript P, which is relative to M Jup, which is the mass of Jupiter. So a planet that has a MP mass of 1.2 says it's 1.2 times the mass of Jupiter. Same with radius. The notation for transits, capital T subscript C is the center point or the midpoint of the transit. This is probably one of the most critical measurements of observations where we are supporting and helping professional astronomers, because they need to know what the center point is. Give you a specific example. I'm heading up a worldwide Hubble collaboration where we're observing 15 exoplanets when Hubble is looking at them, but because Hubble is orbiting the Earth every 97 minutes and is occulting, it can't look at a complete 3 or 4 hour transit. So they've asked us to do the observations, in particular to come up with some key parameters like what's the center point, so that when they're doing their observations in the near infrared, they can understand where they were with their observations. So midpoint, F, capital F is flux, P is period, small a is the semi-major axis. We think of, as we know, most planets are elliptical orbits, and the semi-major axis being a part of that orbital measurement, and these are done in astronomical units, that is to say relative to our distance, the distance from Earth to the sun, which is 1 AU. Are there any questions about that before I go on? Yes?
What about the eccentricity? Is that something we can determine, or are we just going to assume the eccentricity is correct?
Yeah, so the question is, what about the eccentricity? Generally, we assume that for these hot, close-in Jupiters, it's circular. So the eccentricity is, what, 1, I guess. So 0. Thank you. 0. Yeah. Okay. The other thing, just by way of reference, is the relationship of stars to their temperature and luminosity. So this is the famous HR diagram, which shows these are what are called the main sequence stars. Our sun is, right there in the middle. And basically, the point of all of this is that the actual luminosity, L star, is a function of the temperature, that's to say the spectral type. So a star up here, that's an A, has a certain, if it's in the main sequence here, would sort of suggest a luminosity here. Now, let's talk about luminosity for those of you not familiar with it. So when we're looking at a star, and we're looking at the light of the star, obviously there's a lot of things happening between the light of the star and us. It's going through interstellar space, it's going through our atmosphere, it's going through our lenses, it's going through our filters, and then it hits our eyeballs and hits our CCD cameras. So luminosity of the star, think of it as the actual light of the star, which we can, in many cases, can sort of indirectly measure, but unless you're like close to the star. So astronomers do distinguish between, and we'll talk about it in a minute, the apparent magnitude of a star, that is to say what we're seeing, and the absolute magnitude, which is if we're 10 parsecs away from the star itself. And that is the key here then is that if we need to determine the actual magnitude of a star, one of the ways is to look at its temperature through spectroscopy. So we want to measure the absolute light of a star, which we don't really need for purposes here, but I thought it'd be important to distinguish between this when we get to magnitudes. One looks at the spectral type of the star. So in fact, the radius, there's this relationship between the radius of the star, its luminosity, and the temperature through this formula here. And what's important here is that when we get to computing exoplanet properties, one of the things we get from the light curves is, for example, the relationship between our star and RP. Namely, what we get out of the light curve is the ratio of the planet to the ratio of the star. So to determine the ratio, to determine the radius of the planet, we need the radius of the star. And we can look that up, or we can infer it from this relationship. So again, let me restate that. What we get from the light curve is not the actual radius of the planet. What we get is the ratio of the planet to its star. So to get the actual radius of the planet, we need to know the radius of the star. To get the radius of the star, we either look it up or we infer it from its temperature and luminosity. And furthermore, this is just showing the relationship between the mass of the star and its luminosity, and we have in here the mass of the sun and luminosity of the sun. So you don't need to remember all these equations, just simply the fact that getting the radius of the star is critical to actually coming up with the radius of the planet, and there's ways of doing that through that relationship. Yes?
So can the radius of the star, can you just spend your time calculating the radius of the stars?
You can.
Okay.
Yes.
You can do that with amateur equipment?
You can probably get estimates of it, yeah, because if you get the, if you go to the, use the HR, if you have a spectrograph, you look at the spectrum of the star, assume it's a main sequence, look at the luminosity, and then compute the radius. Okay, so now let's go back to our light curve and go back to the key things we talked about earlier. Remember I said that these inflection points are critical here, so let's call them TF, and T sub T is the overall transit time, delta F is the depth. These equations, in some cases, are rather complicated. I'm not going to do them here. I can give anybody a reference to the paper if you'd like, but simply stated, actually the most simplest one is that the radius of the planet, again, is the radius of the star and the drop in light of the curve. That's why it's, again, important to know what the radius of the star is. The orbit, what we really get out of this light curve is the relationship between the semi-major part of the orbit and R star. So again, if we know R star, we can get A. That ratio is a function of the period, the depth, and these 2 points here, the distance of the overall transit and the distance of the lower part of the curve. And the inclination, somebody asked a question earlier, is a function, again, of all of those parameters. This reference here, if you care to go back and look at the math involved in deriving those, you can. But for now, take it that these key parameters here out of an exoplanet observation are a function of these different values. Yes? It's if you do a Google on just Seeger 2002, and I have a copy here during the break, I can show you the reference. It's in one of the astrophysical journals. Yes, question? Okay, so
that's its relative position compared to the equator of the star?
right. So if this is if that's the star, and if from our point of view the planet is transiting directly across, then it's it's a 90-degree inclination from the axis of the star. If it's inclined and the orbit is then sort of, kind of goes, I'm not doing it right here, but if it's inclined, then it's maybe 85 degrees from, 85 degrees, let's say, from that direction. So it's relative to the axis of the star, what the plane of the orbit is. Okay? Okay, so okay, again, the inclination, it's a function of the period, the depth, and just the characteristics of the light curve.
You're not talking about the spin axis of the star, you're talking about
From
the image, how we see it.
how we see it, yeah, relative to our line of sight, right. Okay, so now let's spend some time. This is now key to getting really serious about accurate exoplanet observing. And I would say that a lot of this applies also to other types of high precision photometry, binary stars, and so on. So some of you may be familiar with it, but bear with me if you are. One of the key things to understand is that when we look at a star, it's not just this nice, bright little star, but what we're seeing is a conglomeration of rings that are the so-called airy disk pattern created by the star. So, any point of light, like a star, going through an aperture will create these diffraction patterns. If you remember from the famous double slit experiment where you've got light going through, this is how the wave property of light was determined, is that there's an interference pattern that's created, and one gets different diffraction patterns. When you apply it to an aperture of a telescope, you get diffraction patterns that are just circular. So the main part of that disk, however, is called the airy disk, and then around the airy disk are different concentric circles. But when we see a star, what we see is all of this sort of light kind of conglomerated together. What's really important about this with exoplanet observing is to make sure that we understand what's called the full width half maximum, what the intensity is in this center disk. And I'll come to that in a minute. The formula for that disk is 2.44 times the wavelength of light, let's say like 650 nanometers, divided by the diameter of the aperture. So for example, an 11-inch scope this distance here is 1.2 arc seconds. Is everybody familiar with arc seconds? So a circle has 2 pi radians around it, and so an arc second is 1/3,600th of a degree, and there's a relationship then. So this is a measure of the angular distance of this airy disk. Grady?
Is that wavelength assumed through a filter rather than just a straight?
It depends, right, it's a good question. So the question is this wavelength, depends on, yes, it depends on what filter you're looking through. I just chose here sort of a midpoint of 656 nanometers. But yes, so depending upon the filter and depending upon the wavelength you're looking at it, the airy disk here is going to change. Okay, so again, just to summarize, now notice this is independent of the brightness of the star. So when I take an image, let's say I take a 10-second exposure of a star field, theoretically every star in that field will have exactly the same size of the airy disk. Now, some are brighter, you would say, and some are lighter. Well, how can that be? Well, that's just because there's more light in the outer rings and they're all kind of fused together. But if you look at an image and you measure the airy disk, every star is exactly the same, unless it's perturbed by systematics. That is to say, when we talk about systematics, we're talking about issues with our instrumentation. If, let's say, the field of view is such that you've got dust motes on your field of view, and let's say some stars end up on a dust mote that you haven't corrected and others don't, that's going to affect the light of that star, and so that will affect maybe what we're seeing here. But theoretically, if putting that aside, every star in the field of view should have the same distance here. Okay, is that Bill?
The total light from the star, though, includes both the airy disk and the rings.
Correct. Yes.
So why do you focus just on the airy disk? Why don't you look at the entire
Right.
light?
Okay. So Bill's question is why are we looking just at the airy disk and not the entire light? And if you just save that for 2 slides, I'll answer that question. Yes. Thank you. Okay. In fact, I think it's maybe coming up here. All right. So one of the issues is, and you folks who are doing binary stars know this, is that our ability to resolve 2 different stars, and in our case, maybe planets, but let's take, for example, 2 different stars. The common sort of criteria called the Rayleigh criterion is that if you're able to distinguish 2 stars, if you plotted the intensity of that picture I showed earlier, where you've got these little diffraction rings, then there's the airy disk, and little diffraction rings. The accepted criteria for defining that separation is that if the minimum of this curve is at the maximum of this curve, that sort of suggests that's the ability then to separate those 2 stars. If they get closer, then they're unresolvable. So knowing that airy disk measurement, I said before, that 1.2 arc seconds. Oops, sorry. Go back here. Whoop. So this gives me a measure of the best I'm able to do to distinguish 2 stars. So with my 11-inch telescope, for example, and it's actually half of this, I cannot, no matter what I do, no matter what seeing conditions there are, I'm not going to be able to distinguish anything closer than 0.6 arc seconds. That's my absolute limiting factor. Now, what happens is, in reality, is that the seeing conditions are actually going to make this star, bulge out a little bit. So there's other factors here that are going to kind of spread this starlight more than the ideal. This is the ideal. So in perfect seeing conditions, the best I'm able to do with my 11-inch is to separate 2 stars that are 0.6 arc seconds across. But I've got scene conditions and other things that says really in reality, it's probably like 2 arc seconds. Okay, let me just stop there because I know that's probably. Is there any questions about that? Okay, the key thing to remember is depending upon the size of your telescope, there's an absolute limit as to how much you can separate two objects. That's sort of the key takeaway of all of this. All right, so if we take a look at that middle part of that airy disk, which is this sort of hump here, a commonly accepted measure of the sort of brightness, if you will, of that star is to say what's halfway up the maximum, which is this line here, and what's the width across here of what that maximum, where it intersects the curve. If the curve is very steep, then this is quite small across here. If it's very broad, namely it's, we have a wider airy disk, then the distance here is going to be much larger. So this measure, full width half maximum, is a key measure also for what our observing conditions are like. So in my light polluted skies in Annapolis, generally it's like 3 arc seconds because of the atmospheric turbulence is causing that airy disk to be, that airy pattern to be larger than normal. Here at TDS, what's your typical seeing? 1.5? I don't know. 2? Okay, 2, right. So, down in Chile, in some places, you can get down to 0.5, 0.6. So the point here is that this is important for exoplanet observing because this helps us determine, to I think Bill's question earlier, this is a key measure to knowing when we're going to measure the brightness of a star, we want to measure around the full width half maximum. That's why it's important. This is why it's an important measure for exoplanet stuff. Okay? Are there any questions before I go on? Okay. All right, let's talk about filters. Many of you are familiar with these, with some of this, but let me just run through it. So, those of you who have done deep sky imaging have used, red, green, blue filters, right? For photometric work, there are different types of standard filters that are used. The most common are something called Johnson-Cousins and those used in the Sloan Digital Sky Survey. If you look at, and I tried to put these different plots sort of over each other in the same bandwidth. So for example, at 500 nanometers here, this is between the Johnson-Cousins blue filter and V filter, but it's on this side of the SDSS blue filter, and on this filter here is probably negligible. So the point is, depending upon the filter that's being used, it's going to capture light in different parts of the band. For exoplanet work, there's a couple of considerations. We want to capture as much light as possible because we want to get, as we'll talk about later, a high signal-to-noise ratio. But we don't want to capture a lot of stray light, like background sky glow if there's a moon out. So one of the filters that Astrodon, for example, has come up with, and this was a recommendation a guy named Bruce Gary suggested, is a filter specifically for exoplanet work called a clear blue blocking filter, because what it does is it blocks out, as you see here, most of the blue light to reduce any background sky glow and captures the rest of the light. So a lot of amateurs use this filter. However, for work where we're dealing with professionals, the preference is to use standard filter. And why is that? Well, one reason is so that measurements between two different observations can be more comparable. And if you remember, I talked about limb darkening before. When we're doing the transit modeling, there's a couple of coefficients that need to be included in the transit modeling, and those are based on the filter being used. And there are tables set up for the standard filters, but not for, you know, sort of more exotic filters. So we like to use standard filters, standard photometric filters, for a couple reasons. One is that we can compare different observations. Secondly, we can do a better lookup and estimation of these limb darkening coefficients. So the takeaway from all this is that if you're doing exoplanet work, probably you can get away actually with a clear filter, with no filter. I would not use a red, green, blue filter, but just even a clear filter. But if you're really doing serious stuff, then probably one of these more standard filters. If you're doing casual stuff but want to be a little bit more accurate than just a clear filter, than an exoplanet filter itself. Any questions on that? Okay. All right. Now, if we look at our CCD cameras, there's another effect of how we can capture photons. Let's just go back to filters a minute. So if I have, let's say, a blue filter, I'm not going to capture, it's going to block out any photons in this wavelength here, right? It's going to just sort of give me the photons in that wavelength. If I look at my CCD camera, every CCD detector also has a different ability to capture photons. We call it the quantum efficiency. So again, going across the wavelength, and you'll typically see our CCD cameras that we all use having the same sort of characteristic. You know, captures a lot of light in the green, yellow, and then kind of drops off as we're getting into the near infrared. So now if you say, okay, you've got this filter that's blocking light, you've got the CCD camera that inherently its detector has a certain efficiency. When you put them together, you're going to get the really more accurate curve as to what is being captured. We call it the response curve. So the combination of the filter and the detector will give you what actually is getting through to the CCD. Bill?
Another issue here with regard to quantum efficiency is the ballooning and anti-ballooning
Yeah,
cameras.
right.
What do you recommend?
So the question is, another question here has to do with blooming and anti-blooming cameras. So just very quickly, so a CCD detector that does not prohibit blooming will cause photons to spill over into adjacent pixels. And to answer your question, anti-blooming camera.
You do
Yeah, yeah,
because you get higher quantum efficiency with the non-ballooning.
yeah, yeah. You got the spillover, right. Okay, so it's all about photons. Forget about pretty pictures, forget about, you know, really trying to get gorgeous pictures. It's all about counting photons accurately. So let's take a look at the path of photons from a star. We've got photons coming from the star. Some contribution of it is due to sky background. And that could vary from night to night based on the phase of the moon, based on light pollution, whatever. All of those photons are kind of streaming towards us. But we've got a couple of things happening. We've got interstellar space. Dust's going to knock off some of the photons, right? We've got our Earth's atmosphere, which really is going to knock off a bunch of photons. We've got our filter, which is going to knock off a bunch of photons. We've got the quantum efficiency of our CCD detector that's going to knock off a bunch of photons. And finally, we've got photons that enter what we call the well of our CCD photosite. By the way, I like to use the term photosite and not pixel for this reason. If you take a look at a CCD detector, we traditionally call each little thing that's capturing photons pixels. And I use photosite because there's sometimes ambiguity of a pixel on the CCD detector and a pixel on the picture, which could be two or four of them bin together. So I'm using photosite to mean on the chip and pixel to mean what's on the picture, which could be a combination of binned, where binning meaning we collect together a bunch of photosites into one unit on the picture. So a photosite has a certain well, and we're limited by how many electrons fill up that well. That is to say, how many photons we're able to collect before it gets saturated. Before it's like a well of water, it just starts overflowing. It may, and we're not really counting anymore. So it's critical here in exoplanet work, especially when we're trying to capture photons accurately, is to make sure we don't exceed the capacity of the well, because then we're losing counts, and that's not good. We're not getting accurate measurements. So these go through a ADD converter, and lo and behold, we get pixels that represent the counts of electrons. Those counts are converted to units we call ADUs, analog digital units. Depending upon the camera, I could have maybe 2 electrons per ADU, or I could have 5 electrons per ADU, or I could have 0.3 electrons per ADU. That's called the gain. So the gain of the CCD and the number of electrons collected presents this value called ADU. And this is what we're going to be working with exoplanets. So this is an actual representation of a star I had observed and its ADU counts. And one of the things to notice is, you remember our airy disk pattern, right? There was that high concentration in the middle, and then the sort of bands around it. You can see that sort of represented here, sort of that fallout of it. And you also notice that the sort of center of gravity of the star is not right in the middle. It's kind of offset a bit. That center of gravity we call a centroid. So you'll see references to centroid in exoplanet work when we're putting apertures on stars. We like to put the centroid on the center of gravity. So it might not be what you would think is sort of in the middle here. It's really more, the center of gravity of where the ADU counts are. Okay, any questions about that? Okay. Which is what we're talking about here. So centroid is the center of gravity, and it is important because for a couple reasons. With those of you who do double star, for example, when you're measuring rho, or theta, the distance between two centroids of two stars, it's important to do it from the centroids. So that's important for that reason. It's important for us in exoplanet observing, where we're putting the apertures. Okay. Now let's talk about flux versus magnitude. In exoplanet work, we're going to be talking about flux. And let me distinguish that from, I know most amateur astronomers, most astronomers talk about magnitude. So let's talk about what the difference is. So flux, definition of flux is energy detected per area per second. So if I'm collecting photons, it's not only how many photons, but it's how many per second, and it's how many per area I'm collecting. So it's sort of volume based of what I'm collecting. So flux is a measure of photons being collected. When we talk about the magnitude of a star, we're talking about a measure of its brightness from Earth. And it's relative to always a reference star. So if you ever look in a star catalog, you'll see V magnitude or I magnitude, because there is no such thing as the apparent magnitude of a star. It depends on what filter you're looking through, and also what reference star you're using. So it's relative to reference star and a particular wavelength, namely what filter. And this is the definition for it. It's a function of flux between the ratio between the two stars. And you can blame the Greeks for it, but magnitude is a difference of 5 magnitudes is 100 times brightness. That was sort of visually what the Greeks sort of thought of, and that's stuck with us now. So, for example, a flux, namely brightness, of 1,000 relative to a flux of 10, and if that star whose flux was 10 had a magnitude of 12, you plug it into the formula, and the magnitude of our star of interest is 7. So, and magnitudes, of course, go in opposite directions from what we would think. A magnitude of a 12-star magnitude is fainter than a 10-star magnitude. But the reason I wanted to just talk about this relative to exoplanets is because I just wanted to show that relationship, but to again make the point, what we're going to be talking about is flux and not so much magnitude. Yes?
I like to tell people that Vega is 0 magnitude,
Yes.
and the Greeks came up with that. We all know.
Good point. Yes. What was your name? Yes. Made the point that Vega was sort of the standard 0 magnitude, and that's what the Greeks used to everything relative to that until somebody realized we had to come up with the magnitude of the sun, which we then went negative. But anyway, it's another story. Okay, so that's apparent magnitude. So that's what we are seeing here on Earth through all this stuff I said earlier. But now getting back to absolute magnitude, what astronomers, again, define it as if we were 10 parsecs from that star. That's sort of the standard way of coming up with what the absolute magnitude is. I'm not going to say anything more about absolute magnitude here. I just wanted to, again, sort of go back to the point that we need to be accurate when we're talking about, especially in any papers that are being written, we're talking about absolute versus apparent magnitude. For example, just last week, I'm working with a postdoc at Harvard on some exoplanet stuff, and he sent me a question about how can we use Astro Image J to get the absolute magnitude of a star? And I wrote him back and I said, do you really mean the apparent magnitude of the star? He said, yeah, the apparent magnitude of the star. So the point is that we need to be very precise when we're talking about some of these factors because, there's a world of difference between the two. Okay. And as I said earlier, ADUs is a proxy for flux. Flux was amount of energy per area per second. ADUs is a proxy for the count of photons per area, that's to say per pixel. And the exposure time in this case is what we divide that and you get the per second. Okay, now let's talk about exoplanet observing, what equipment and software are needed. So this is my setup, and I thought I would do this just to show you one sort of extreme and how actually it could be simplified. So this is just my backyard setup. 11-inch Celestron scope on a permanent pier, indoor electronics on a Losmandy G11 mount. The image trained goes through something called an active optics unit. This is entirely optional. Active optic unit is entirely optional. What an active optics unit is doing is because of the turbulence of the atmosphere and the star is really kind of moving around like that, what it's doing is it's a piece of glass that is constantly, several times a second, changing tip direction to compensate for the turbulence in the atmosphere, to try to improve or try to compensate for some of the seeing conditions. I say it's not mandatory because I just like it because it just helps me get better effective seeing, if you will. But those of you with good seeing conditions, maybe a TDS, don't necessarily need it. But that is something available now for amateur astronomers. It's not like the guide star and adaptive optics that professional astronomers use, but the idea is sort of the same, compensating for atmospheric turbulence. Yes. What kind of what? A gizmo thing. Gizmo wrap. Been out there for 3 years. Winds, rain, hurricanes, no problem. I do take the electronics in, but everything else, I just keep it there. No need to pull or line every night, all that good stuff. So the next thing in the image train is the guide camera. And I cannot emphasize more the importance of auto-guiding with doing exoplanet observing. By that we mean the goal is to stay on the same pixel for 4 hours. Maybe 2 pixels for 4 hours. And I tell you, I can do it. I mean, you'll see some of the stuff I do it. So imagine this big mechanical stuff, scope and everything else, tracking a star for 4 hours, putting aside a meridian flip, tracking a star for 4 hours, staying within 1 or 2 pixels. And I can tell you, you can do it. Okay, because you don't want that star to wander around much on your detector because it may land on a dust mote if you haven't done good flat fielding. So the goal is keep that star. Again, we want accurate count of photons. That's what all this is about. So not to let the star wander. So guide camera, so it's an off-axis guider, so the light comes in here, there's a little pick-off mirror, goes to that camera. That feeds back inside software running on the PC that feeds the active optics unit to do its little thing. And if it can't compensate enough, it'll cause then a change in the mount, typically in the right ascension axis. So the point is, the beauty of this active optics thing is I can go for a long time without moving mechanically this mount, because that's then a bigger process. Yes?
Do you have any reference to it? I know that SPIT had an active optics unit at one point. Which one?
Yeah, so the question is what active optics unit do I have? It's a Starlight Express active optics unit. So the guide camera is used to stay on a guide star. So if you're looking at your field of view and you have your target star, you pick somewhere in the field of view another star. You, using software, free software, PhD2 I use, you put your crosshairs on that guide star, and if it moves a little bit, the software will send a command to the active optics to do a little shift to keep everything centered. And you'll just see that sort of happening, all night. The guide camera is fairly sensitive camera. I've used some of the cameras used for planetary imaging. What I use is a Lodestar X2 camera, again, Starlight Express product. So that's critical for exoplanet observing, to keep that target star on the same point of the detector. Then go through a filter wheel that where I'll be able to change filters. Typically, I'll stay with one filter for most of the observation. Then to my monochrome CCD camera. The reason for monochrome, obviously, to use different filters. So this is the image chain. Now, just to show it a slightly different way, I'll show in a minute. But let me go through a couple other things. All of these are characteristics of a CCD camera that are important for exoplanet observing, because some of these affect the uncertainty that we're measuring. Let me go through these. Gain is used to convert, as I said before, the electron counts to ADU counts. Read noise is when you read an image, there's a certain amount of noise that comes with it. Dark current is sort of background noise that's there. These two are used in the exoplanet modeling software to come up with what the uncertainty is for the measurements. So that's why it's important to understand what those are for your CCD camera. The greater the amount of noise here and dark current, the greater the uncertainty of the measurements. So the idea is to, for the CCD camera you're using, to have as good a camera as possible with respect to those 2 points. The other characteristic is the size of, and I didn't even abide by my own rule here. I should have said photosite, right? See, I even do the same thing, right? The size of the photosite. And the reason for that is because That plus the focal length of the telescope will tell the so-called image scale, how much of the sky each photosite is seeing. And the reason that's important is because we want that light from that airy disk, especially from the full width half maximum of that airy disk, to be spread across multiple photosites. So if we have all that light concentrated on one photosite, that's not good. So we want to make sure it's spread across multiple photosites. And I'll describe in a minute how to do that. Yes?
And is there a recommendation for this type of work in terms of the minimum or maximum size of those photosites?
Okay, so the question is there a recommendation as to the minimum maximum size of the photosites? The answer is no, because it depends on the telescope, the focal length, and so on. The rule of thumb, however, I'll just sort of jump ahead a bit, is that the full width half maximum of the star should be spread across 3 to 5 photosites. So you need to calculate your image scale, what your full width half maximum is, and figure out what the number of photosites are. Yes?
For that reason, is it ever advantageous, even if you're in a good seeing site, to defocus
Yes.
on purpose?
You're like 3 slides ahead of me. Yes.
Okay.
Yeah, so the question is it advantageous to defocus? And the answer is yes. That is a common technique used to, especially if you're looking at a bright star and you want to spread it across because your image scale is too small or because it's too bright and you're going to saturate. So defocusing is sort of alien to all of us used to do pretty pictures, but defocusing here is in some cases a good thing. Yes, Bill?
You haven't mentioned well depth. Is there an optimal well depth you have for your camera?
Yeah, so the question is, I haven't mentioned well depth. Is there an optimum well depth? I did mention earlier that the key is you don't want to obviously exceed the well depth, but as you know, each camera is going to be different. I would say that's a secondary consideration. I think it's more 100,000. Mine's 100,000. Yeah. Number of pixels, a combination of these two gives your field of view. Yes? I'm sorry, I can't hear you. Yeah, okay. So the question is, some of the scopes have a slight amount of astigmatism. Where the effect is, what you want to do is, in addition to the target star, as I said earlier, you're going to be picking comparison stars. So you want to make sure that the comparison stars are in the field of view that is not being affected by collimation issues or aberration or astigmatism or anything else. So it more has to do with your ability to capture comp stars that aren't affected by those factors or that would be an effect. Oh, you're talking about if you defocus. Yeah, no. The defocus we'll show later is, how can I explain it? It's really just spreading the collection of photons across photosites. And as long as your optics aren't having an effect there in some strange way, it shouldn't matter. Now, maybe I'm missing your point. Maybe we can talk during the break more about it. But so with my system, the question is how many arc seconds per pixel? 0.45 unbinned. The other factor, as I mentioned earlier, is quantum efficiency. We are not able to, unfortunately, to see much in the infrared. I wish we could, because there's some interesting things we could do, because most of our CCD detectors drop off before the infrared. So again, the quantum efficiency, and nowadays some of the modern CCD cameras are, have real high quantum efficiency, at the critical wavelengths that they're operating at, 70–80% quantum efficiency. All right, let's talk about signal to noise and what each represents. So signal is the counts of the photons that we're detecting. A signal also is bad stuff, like dark current. It's an unwanted signal. And the other one is, the other unwanted signal is bias, which is if you take a zero exposure, there's a certain bias factor that offsets the ADU. It's very small, but nevertheless it is a factor. So all of these contribute to signal. Now, by noise, we're not talking like noise you would traditionally think of. We're talking about uncertainty. So the question is, what are the uncertainties, which is really, when we talk about noise, that's what we mean, uncertainties. Well, one is the uncertainty in photon counts. That's to say, if you're looking at a star and all else being equal, just the uncertainty in the photons arriving at you, there's a certain uncertainty there. There's some noise in the dark current. That's to say, some uncertainty there. There's some uncertainty when we're reading out data. So the key then is to increase the signal and reduce the noise. And so understanding, as I said earlier, about dark current, readout noise, bias, and all the rest will help us determine where we are with respect to getting a good signal-to-noise ratio, what we can do about it and what we can't do about it. So when we hear signal-to-noise ratio, the important thing to remember is this is what's going in the signal, this is what's going in the noise, and that's what we need to achieve. Increase the signal, reduce the noise. Now, the other thing that affects exoplanet observing is the telescope itself, the optical tube assembly. And there's many different kinds, many of you are familiar with. All of these factors here, the aperture, focal length, whether there's a central obstruction, whether the optical tube itself has a lot of thermal currents in it, which is going to affect sort of, you almost think of it like a local atmosphere, if you will. How accurate the focusing is, whether it's well collimated, any spherical aberration, all of these affect, again, our ability to collect photons accurately. And the point is just to be aware of it and minimize as much as possible all of that. All right, so if we take a look at again, my bad, this should be photosite. If we take a look at a photosite and look at what's the angular amount, what's the angular separation, not the angular separation, what's the angular scale that photosite can take, is by this formula here. And you can see it's a function of the size of the pixel, or the size of the photosite, and the focal length. This, as I said earlier, is really key to understand. So in doing exoplanet work, the first question is, what's your image scale? Because, again, we want that full width half maximum to be spread across multiple photosites. So, for example, if your image scale is 0.5 arcseconds and your full width half maximum at your seeing conditions is 2, then that says that full width half maximum is going to be spread across 4 photosites, which is good. If you're in really good seeing conditions, like Chile, and your full width half maximum is 0.5, and your image scale is 0.5, that says most of that starlight's just going to land up in one photosite. Not good. So, in fact, in Chile, you'd want to probably defocus to spread that light then across multiple photosites. So understanding your image scale is really key in exoplanet work. The other thing, of course, is field of view, which is if you combine all the photosites together on your detector, how much sky am I looking at? With my setup, for example, my field of view is about 14 arc minutes. So I can see 14 arc minutes of sky. And what's important there is because then that tells me how much ability I have to pick up some comparison stars in that field of view. So these are quite easily computed based on those formulas. Okay. And mount characteristics. Everybody has different kinds of mounts. German equatorial mount, those of you who have one know that as you're tracking a star, when it gets to the meridian, you got to do a meridian flip, you lose the target, you get back on target, and you lose, a couple minutes or whatever. So German equatorial mount, in some cases is good, but in some cases for the kind of work we're doing is not optimal, but it's doable. There's ways of compensating for that, and we'll talk about that later. Fork mount is probably the best in that you don't have to do the meridian flip. You're able to track a star as it's going across the meridian. Every mount has some kind of periodic error. In some cases, so by periodic error, what we're talking about as the mount is, the gears are compensating for the rotation of the Earth, and there's a little worm gear that's turning the bigger gear. If it's not quite accurate, there's going to be some error introduced every period that worm gear turns, and that could affect, for example, the wandering of that star. We like to keep the periodic error, actually the accumulated error, as I said earlier, with 1 or 2 pixels. So if you have a mount like I do, that without any auto guiding or compensating, my mount periodic error is about 8 pixels. And it's not great, it's not bad, but it's still not good enough. So when I do auto guiding and with my active optics, I can get down to 1 pixel or less of movement. So understanding periodic error of your mount and compensating for it, and there are most mounts now, you can also do periodic error correction, where you actually do a history of what that error is, and then internally in the mount, there's ways of compensating for it, is always a good thing. So reducing periodic error is a good thing. Any gears that operate together, if they're operating in the same direction is fine, but if they have to go in the opposite direction, there could be a lag, that is to say backlash. So for here, because we're not compensating too much for, as the star is rising, as the Earth is rotating and we're compensating for the rotation of the Earth, we're changing mostly direction in right ascension. But because of atmospheric seeing, the star may also wander in terms of declination. And if we're not compensating for that, and we're trying to do that either in software or otherwise, and there's a lot of deck backlash, there's going to be a delay before the compensation takes place. So minimizing deck backlash, again, has the effect of keeping that star as tight as possible on the detector. And deck backlash can be compensated in a number of different ways, either software or just fine-tuning your mount. Balance is important because if you're not properly balanced, again, there may be some effect, especially in right ascension direction with accurate tracking. Polar alignment is also important, and it's important for this reason. Even if we're doing guiding and using active optics and we're compensating for the direction of that star, if the scope is not polar aligned, there's going to be a natural drift of that star in declination, which means more compensation having to be done. Is Cerny here? Who was one of the observers? Sina. Yes. Sina and I had a little email exchange about you have, I think, a Paramount. Or somebody I was talking with has a Paramount mount. Very good mount, excellent periodic error correction. And the correspondence I had was, the question was how long the exposures are. And I said they could be 5, 10, 30 seconds. And the response was, well, that's great because I have a very accurate mount. Well, that could be true with respect to periodic error, but if it's not polar aligned, what's going to happen is over time that star is going to drift across the detector. So the point is that even with good, even perfect periodic error, if the mount is not polar aligned correctly, that star is going to drift. So all of these mount errors can build up to a wandering star. Okay, let me just see if there's any questions about any of that. Okay. Okay, so now we pull it all together, and what we've got is from the star going through possibly a focal reducer. What that does is it effectively changes the focal length of the telescope. I don't have one. Some folks do. I also do have a rotator to make it easier for being able to change the orientation of the camera. I don't know what I do with my little pointer here. And then through the active optics unit, and again, optional, through the off-axis guide or the CCD camera, and so on. So that's bringing it all together. Auto-guiding. Again, several forms of auto-guiding. Some folks use a separate little refractor scope to pick off a guide star. And the problem with that is could be flexure between that guide scope and the main scope, which doesn't present as good guiding as if it's what's called off axis, meaning it's in the line of the optics, but there's a little pick-off mirror, so you're not getting any flexure. That's what I do. Some cameras, some SB cameras, for example, have a guide chip next to the main chip, and then there's also something called on-axis guiding, which actually the light comes in, and there's a piece of glass that's a refractive thing that will actually it's sort of a I don't know, some kind of refractive mirror or something that sends the main light up to the imaging camera and passes, I think it's like some of the infrared light through to the guide camera. So it's a different kind of doing off-axis guiding. But the point of all of that is that that it's really important to do auto-guiding in exoplanet work. Yes? No, the question is auto-guiding and tip-tilting redundant? No, they work together in this sense. The guiding software, PhD2, is driving the tip-tilt active optics. So I need that PhD2 auto-guiding software to do that. When I can't compensate enough with, if the star really starts wandering past, then I do need to send the traditional pulse to change the guiding in the mount. So they all do work together. So think of the active optics as sort of the first line of defense, and then if that doesn't work, then the traditional pulse to send the mount a correction. If the periodic error is small, you still would have seeing effects and drift due to if it's not polar aligned. So accurate, perfect periodic error does not get away from wandering due to seeing or drifting due to being off due to polar alignment. Okay, these techniques, preferably a sensitive guide camera. The mounts, all mounts these days, use ASCOM. There's two ways of controlling guiding. Pulse guiding is the preferred method for guiding because it is also sort of a two-way path as opposed to the more traditional, what's called SD4 kind of guide interface. The software that's used is, again, I use PhD2, but all the normal kinds of image capture software have some kind of guiding, MaximDL, SkyX Pro. But they all do require some kind of initial calibration because you can imagine, depending upon the orientation of the CCD camera, for example, if a star wanders in a certain direction on the CCD camera, that may mean a different kind of correction to the mount as opposed to if the CCD is oriented differently. So there's initial calibration done. And the other thing is that once I pass and do a meridian flip with a German equatorial mount, I've got to change the way that the calibration operates, and that's done in many cases automatically on most mounts that are ASCOM compatible. So takeaway from all of this is auto-guiding, especially off-axis guiding or any of these other three, are critical to keeping that star on the right point on the detector. Okay, so let's talk about reference locations with respect to time. If I have a star sitting out here and I'm trying to measure a transit, the time, the beginning of a transit on Earth, I say, okay, there's the beginning of the transit, okay? But let's suppose there was a parallel Earth 6 months away on this side of the orbit, okay? The distance from that place in the orbit to the star is going to be different. So a hypothetical person there is going to measure the time it's going to be a different time for where they measure it. Furthermore, if I happen to be on the sun, I'm going to measure it differently as well. The point of all this is that for exoplanet work, because of how critical it is to do the timing, it's important to know what's our reference time frame we're using. Those of you familiar with the normal kinds of astronomy time, have heard of, using universal time, Julian date universal time, which is, Greenwich Mean Time effectively, which is, as if we were in Greenwich, England. What astronomers did was they realized that that didn't account for where the Earth was in its orbit. So they came up with something called heliocentric Julian date time, which is if we were on the sun, what would be the time? And there's ways of converting from universal time to heliocentric time. Okay? But then astronomers realized that's not even good enough, because if you remember from that wobble thing, the center of gravity of our solar system is not smack dab in the middle of the sun. It's a little bit off. So the other reference location is something called the barycenter, which is the center of gravity of the entire solar system. That's not even good enough, because the solar system is moving and Einstein's, time dilation and all that stuff. So there's even a correction to barycenter. But the point of all this is that for exoplanet work, what we like to do is to have our time base barycentric. Okay, so, yes.
Considering the distance of stars, what is the actual time difference?
You're like one slide ahead. I'm about to show you that right now. Well, that's okay. It's on the order of minutes is the answer. Yeah, I'll show you that in a minute. So if I said, what time is it? What would we all say? Well, I look at my watch, it's 11:47 and 35 seconds. Okay, but that's that's San Diego time. Yeah, okay. But I'm using my watch, right? So there's two factors there: where I am and what clock I'm using. Okay? So let's take an example. The point here is that time is a function of where you are and what clock you're using. So local time, let's say here in San Diego today at 1300. You might say that's great. The equivalent universal time, I think we're 7 hours behind right here in San Diego. So universal time is just at 7 hours, right? Now, let's just convert that to Julian date, since that's generally what astronomers use. So universal time, Julian date is that. But now let's take a look at what the heliocentric time equivalent is of 1 o'clock here. And it's that, which is 6.4 minutes difference. So, Bill, your question, that's the difference between the universal time and if we were in the center of the sun. The barycentric difference is that, which is an extra 1.1 minutes. So the difference between our local time here and what astronomers really want to have as the measured time is on the order of 7.5 minutes. So you can see it's not insignificant. Right. So, so to calculate this, and I have references, online web pages that you could go to. And by the way, the software I'm going to talk about tomorrow does this automatically. Heliocentric, as you would imagine, is a function of where the star is. Its right ascension and declination. So this is Kelt 1, which is the object we're going to be talking about analyzing tomorrow. From here in from universal time, that difference is based on that. Barycentric is a function of not only where the star is, but where we are and our altitude. So barycentric is a little bit more complicated. But again, AstroImage will take care of all this. The other factor here, you notice this little subscript, TDB. There's barycentric Julian date time, then there's barycentric Julian date time, barycentric dynamical time correction, which has to do with, and that's on the order of milliseconds with, you know, time dilation and all that good stuff. So this is the key measure when we're measuring exoplanet transits as far as our timestamps. So the software will convert, our image capture software on our computer will put something like that in, but the AstroImage software we're going to talk about tomorrow does the conversion.
One point that might be worth making is it is irrelevant what the distance to the star is. And that star might be 10,000 light years away. The issue is what direction is it. If the star transits at midnight, so now the light from the star gets to me before it gets to the sun. If the star transits at noon, the light gets to the sun and then gets to me. And that, you know, the distance from the sun to the earth is about 8 light minutes. So that's, it's the direction, not
Yeah,
the distance
right.
of the star.
Yeah, you'll notice there's nothing here about direction. It's all where it is in the sky relative to us. Yes?
The barycentric dynamic time, what is the source of that difference, the dynamic part?
It's, again, the time dilation. Einstein's time dilation is as our solar system is moving. Yeah.
Our motion relative to the barycenter or
The barycenter relative to the star itself.
velocity?
Yeah. Yeah, so it's our solar system, the barycenter of our solar system, moving relative to where the star is. Yes?
What time, just for reference, does the Julian day begin?
I can tell you that.
In the old days,
Yeah.
the military uses Julian day too.
Yeah.
But in the old days, the military starts at 2400 too. So in the middle of the night,
Oh.
it's inconvenient for astronomers, so to use the different.
Oh, I'm sorry. Maybe I didn't understand your question. So this, for example, is days. So that's right. And this is, you know, fractions of a day. Generally, the beginning of a day is, you would see a 5 there, for example. I don't know if that's answering your question, but we can talk offline if that's not answering it. Okay, so it's important to know in what time base are the predicted transit times. So, for example, if I go online and I say, Kelt 1 tonight is going to begin transit at this time, if I don't know what that time is based on, I could be off by 8 minutes, right? And in fact, the interesting thing is when you go back to some of the early discovery papers, they were very lax about what they were defining their time base in. Some would define it not at all. Some would define it as universal time. Then folks started to get a little bit more accurate. But so not only understanding what the predicted time is so you could start your observation on time, but also what are you recording so that when you give it to the professionals, they know what you're recording it in. Okay? So that's key for both reasons. All right, so now, how do we measure time? Well, on our computers, every computer here, there's a little time drift, right? So to get accurate time stamps, we need to make sure our computers that are capturing images and putting those timestamps on them are operating accurately. And the way to do that is to update our computers based on atomic clock, and there's freeware to do that, Dimension 4. I have it loaded up constantly. You can set how often you want it updated. I update mine every 2 hours, for example, to stay within milliseconds of the atomic clock. Because again, the accuracy, we're trying to get these transit times, is important. And the reason it's important is because something I said sort of way at the beginning, which is if we're doing what's called transit time variation studies, namely, is there a little change in the time that that transit started? That could be important because that could mean that there's another planet that's causing that perturbation. So doing accurate timing is important. There are some transit time variations, for example, that are on the order of a couple minutes that we amateur astronomers, if we did things really accurately, could be able to determine. So transit time variation studies is something amateur astronomers can contribute to the professional community to if we're doing things accurately. Okay? In fact, the Kelt 1, I chose that for this reason. The discovery paper had, a time when the transit occurred and the period of how long before the next transit. You use those two to extrapolate out till 2016 when that transit's going to take place. Well, come to find out, I think just a couple months ago, that the original calculation for the period was off by about a second. And since that original discovery, that transit time now is off by 30 minutes. And in fact, one of the things we were going to do with Kelt 1 to contribute to real science is to take an actual observation to confirm what that current transit time is to get a better definition of the ephemeris of that planet. So here, we could have had the ability to actually do some real science tonight by helping to refine that transit begin time. When I did it a few days ago, indeed, it was off by about 30 minutes. And we'll see that tomorrow. Okay, so this is Dimension 4. It's really user-friendly. You pick the Internet Time Server site. I picked the U.S. Naval Observatory. And what you can do over time is you can see the variation of how much drift you had on your clock. And you probably can't see the scale here, but this is 1 second. So over this time, you can see that it was updating. And this is over a period from July 28th till September 26th. You can see the updates and corrections it was making. Okay. Okay.
What was the delta time scale?
1 second. From that line to that line is 1 second. Yeah. So that's, plus or minus 1 second. So 2 second sort of offset. Which could be a big deal if we're doing transit time variations. Okay, this might be a good place to stop, I think. It's noon before we get into how we actually do light curves. And then we'll pick it up. What time do you want to restart, Pat?